Good morning, welcome to new lecture. Today I will solve some compound beam and I will talk about compound beam and you will see how we can find reactions for compound beam. So compound beam, for example, this is one beam. We call it simply supported beam, or this is one beam. One end is fixed, another end is free, we call it cantilever. If we combine three beams, but if we combine these beams in a way, we can find reactions using equilibrium equations only. We call it compound beam. For example, assume we have this system. This is kind of compound beam. So if we combine three beams, we call it compound beam. We are able to find reactions for these kind of compound beam using equilibrium equations. Later on you will see in another courses, if number of reactions is more than number of equilibrium equations, with only equilibrium equation we will not able to find reactions. That is another topic. But in static course for compound beam, always we are able to find reactions using equilibrium equations. Let's look at the first example. Assume we have this beam. This is roller support. Point A. Here we have hinge B. Then we have fixed support. And here we have concentrated load. The magnitude of the load, it is 3 kips. This span is 8 feet, and this span it is 12 feet. This span is subjected to non-uniform distributed load, and the maximum magnitude it is 1.5 kip per feet. I want to find reactions here. In any location, if we cut beam element for 2D in plane structure, so if our structure it is in plane structure or it is in 2 dimension, in that case in any section we cut the beam, we need 3 internal forces in order to satisfy equilibrium for that segment. One of them it is axial force, another shear force, another bending moment. Hinge, according to the definition of the hinge, we release one internal force here. It means we know one internal force over there. That internal force it is bending moment. Always bending moment at hinge it is equal to 0. Hinge definition means no resistance, no reaction against the bending moment. So, for example, if you don't have this support, this AB part can rotate respect to this point B freely. No resistance at point B. So we know bending moment always at hinge is equal to 0. Now, if I want to find reactions, let's for example, I want to find this reaction, AY, A point A reaction in the Y direction. I can write summation of moment respect to point B equal to 0 for only left side of the structure. Once we are writing equilibrium equation for left side, we will not care about the right side. Forget about right side. Assume we don't see the right side of the beam. After point B, we don't see the BC part. We are writing summation of moment respect to point B Or if I want to represent precisely, I should draw free body diagram. Here it is AY. Here we have external load. At point B, moment is 0, only we have axial force and one shear force perpendicular to the B, we can show with BY. Now this is free body diagram for left side. In this free body diagram, I am writing summation of moment respect to point B. That means AY times 12, it wants to rotate this piece respect to point B clockwise, so it is negative, plus the area underneath of this triangle will be resultant force, so it will be 1.5 times 12 times half. This is resultant force. The location of the resultant force for triangle distributed load, it is in centroid, and the centroid distance from point B, it will be 1 over 3 times 12. 1 over 3 from point B, 2 over 3 from point A. From this side it is 2 over 3 times 12, centroid location. From B side it is 1 over 3 times 12. So because we are taking moments respect to point B, I should multiply to this distance. That will be 1 over 3 times 12. This moment, rotate this piece AB respect to point B counterclockwise. If you remove this support A, you will see this piece will fall down. It will rotate respect to point B counterclockwise. So it is positive is equal to 0. From here I can find AY. AY will be equal to 3 kips. Now, if I write summation of forces in vertical direction, I can find BY. So AY plus BY minus 1.5 times 12 times half is equal to 0. From here I can find BY is equal to 6 kips, because AY it is 3 kips. If I plug here, this will be 3 here. I take to other side, the answer will be positive 6 kips. After finding AY and BY, so I know this fraction. Now I can show here AY is equal to 3 kips, BY is equal to 6 kips. Now, we know if we have triangle force, 3 kips will transfer this side. So, here reaction will be 3 kips. 6 kips will transfer this side. So, if I cut at point B, reaction BY will be 6 kips. Reaction is 6 kips, but action, the things this external load apply at point B, it is action. It means it is in inverse direction of the reaction, that is 6 kips. Now I want to find reaction at point C. Because other side I found it, I can remove it. So here I want to find CY. CY, summation of force in vertical direction, minus 6 minus 3 is equal to 0. From here CY will be equal to 9 kips. If I want to find this moment reaction at point C, I can take moment respect to point C. That will be negative MC because it is clockwise. Positive 6 times 8 6 times 8 plus 3 times 4. From 3 to here it is 4. 3 times 4 is equal to 0. So from here MC will be 6 times 8, 48 plus 12, that will be 60 feet cubes. So this is the way we should approach to compound beam. Let's look at another example. Assume we have this beam. A, B, this is 3 meters. Here, point C, pay attention. Beam is continuously passes from point C. So, beam is continuous, C hinge is here. The concept of this, it is different from this. Compare. Here, this hinge is divided beam to 2 pieces. Here beam is continuous. Here we have internal moment. Here internal moment it is 0 because left and right they can rotate separately. Here they cannot rotate separately. So pay attention to those details. Here point C, then we have point D, point E, point F. External load 12 kilonewton. This is 4 meters, 2 meters, 6 meters, and 3 meters. Here we have another external load. It is uniform distributed load. The intensity of the load, it is 3 kilonewton per meter, and it is from B to D. I want to find reactions. Look at the beam to see which side it is easier to approach to this problem. Here, if I want to find E, Y, it is very easy. Why? Because I can take moment of this part, right side, respect to point D. Or free body diagram, if I draw it, this is EY. Here, point D, I am cutting, so here I have DY. And here I have 12 kilonewton. So from here to here it is 3 meters. From here to here it is 6 meters. Point D, point E, point F. In this free body diagram, if I take moment respect to point D, what I have EY times 6 minus 12 times 9 is equal to 0. I'm taking moment respect to here. This is hinge. I know moment should be equal to 0. So EY times 6 minus 12 times 9 is equal to 0. Or in this free body diagram, EY times 6 minus 12 times 9 is equal to 0. From here, I can find EY. EY will be equal to 18 kilonewton. Now in this free body diagram, if I write EY plus DY minus 12 is equal to 0, summation of forces in vertical direction is equal to 0. EY plus DY minus 12 is equal to 0. Because EY is 18, if I plug here, DY will be negative 6. negative 6 kilonewton. Negative 6 kilonewton means this initial direction I assumed for dy is wrong. I assume upward. It should be downward. So I can change the direction. And this will be 6 kilonewton. So now if I draw this part, free body diagram, one more time. I'm cutting from here for this part. Look at the free body diagram. This is point D. Here I have 6 kilonewton downward. Here I have 12 kilonewton downward. Here point E, I have EY 18 kilonewton upward. And this is 3 meter. This is 6 meter. You see, summation of force in vertical direction is equal to 0. 6 plus 12 minus 18 is equal to 0. So for this part, I found everything. Now, this dy, you see, this dy, it is reaction. Reaction, it is downward. If I cut from here, this dy, you see, downward. So dy for other side should be upward, because if we attach together downward, upward, it should be cancel each other. We will get 0. We will have the continuous structure. So now I find in this free body diagram dy downward. So the action of the left side to the right side will be upward. Now, if I remove this part up to here, because I found everything, this dy should be upward 6 kilonewton. In another free body diagram, it was downward. Now, let's look at to this part. Now again I can cut from point B. I can draw free body diagram. Here I have Cy. I have 6 kilonewton dy upward. Here assume By for now upward. This axial force, no problem. You can put in any direction you want. And this is distributed external load. Intensity of the load, it is 3 kilonewton per meter. And from here to here it is 2 meter. This is 4 meter. Again, this is another free body diagram. In this free body diagram, if I write summation of moment respect to point B, I have Cy times 4 plus 6 times 6 minus 3 times 6 times 3 is equal to 0. I'm taking moment respect to point B. Cy times 4, it wants to rotate this beam respect to point B counterclockwise positive, plus 6 times distance up to point B, again rotate counterclockwise positive, so 6 times 6 minus, because this external load respect to point B will rotate this beam clockwise, so negative 3 times the length of the load. It will be resultant force, so 3 times 6 times the resultant force location, it is at centroid of the rectangular, up to point B, because entire this it is 6, this will be 3. 3 times 6 times 3 is equal to 0. From here you can find Cy is equal to 4.5 kilonewton. So after I found Cy, now I can write summation of forces in vertical direction. So I can write Cy plus By plus 6, By plus Cy plus 6 minus 3 times 6 is equal to 0. Because Cy I found it is 4.5 kilonewton. If I plug there, I will find By. So I can find By. By will be 7.5 kilonewton, and upward direction I selected, it is right. So now let's see. Now after I found the By, I can remove this part as well. So in this free body diagram, By was upward, so here we will have the same By, magnitude is the same, direction is in inverse direction. I will plug By downward, so in this part Ay, if I write summation of force in vertical direction, will be 7.5 kilonewton upward. If I take moment respect to point A, I can find MA. MA will be 7.5 times 3, that will be 22.5 kilonewton meter. Next example. The next one, it is this beam. Point A, point B, point C, 4 feet, 2 feet, 3 feet. Here, this part is subjected to uniform distributed load. The intensity of the load, it is 400 pounds per feet. At point C, I have one concentrated moment. The intensity of the moment, it is 900 pound feet. The intensity of the moment, it is 900 pound feet. Now I want to find reactions. Again, I will cut this to the two piece. One free body diagram for segment BC. This will be By, this will be Bx. This is, I have support, so support reaction Cy, external moment 900 pound feet, this length, it is 3 feet. If I take moment respect to point B, here without free body diagram, you can do that for right side again, the same thing, Cy times 3 minus 900 is equal to 0. Cy times 3, distance, I am taking moment respect to point B. Cy times 3 minus 900, it is moment, you will not multiply to anything. Minus 900 is equal to 0. Cy is force, times distance will be moment. Respect to point B, it will be moment counterclockwise, so positive. Cy times 3 minus, this is respect to point B, again it is clockwise, so minus 900 is equal to 0. From here, Cy will be equal to 300 pounds. Now, summation of forces in vertical direction is equal to 0. By plus Cy is equal to 0. Cy I found, it is 300. So from here, By will be equal to negative 300 pounds. Negative 300 pound means this initial assumption, it is wrong. This should be downward 300 pound. This is for part BC. Now I can remove that part because I found everything. Look at to the next part. BY downward was for BC. So for AB it should be upward in inverse direction of that. This will be 300 pound. Now I want to find AY and MA. Summation of force in vertical direction is equal to 0. This means AY plus 300 minus 400 times 4 is equal to 0. From there I can find AY is equal to 1300 pound. So AY will be equal to 1300 pound. Now if I take moment respect to point A, I can write MA plus 300 times 6 minus 400 times 4, this is resultant force, times 2 respect to point A is equal to 0. From here I can find MA is equal to 1400 pound-feet. Okay. Okay, homework problem. For next session, in this structure, assume we have one column. Here we have pin support, and at point B here we have cable, and again another side of cable at point C we attach to the hinge support, point B, point A, point E. This is 6 kN, 3 meters, 4 meters, 3 meters. Okay, we have one continuous column. If we don't have this cable, what will happen? It will rotate respect to point A. It will rotate like this and it will fall down. I am pulling with 6 kN at point E. I attach one cable from point B to the C. What is internal force in cable BC? How much force will develop inside of this cable? And it is clear, inside of cable we will have only axial force. Cable, it is a structure. It cannot sustain against bending moment. No resistance against bending moment. No resistance against shear force. It can only sustain against axial force. And even you cannot apply compression force. You can apply only tension to the cable or rope. This is cable or rope. So cable or rope will resist against only axial force, and that axial force should be tensile force. It works in tension only. Find that tension force. Another one, you have this beam, point A, point B, hinge and roller support, 6 kN here. This part we have triangle load, The maximum intensity is 12 kilonewton per meter. 6 meter, 3 meter, A, B, C. For this beam, first find reactions, then draw bending moment diagram and shear force diagram. So, for this beam, first step find reactions, then draw the shear force diagram and bending moment diagram. Another problem you should solve. It is one cantilever beam. The beam length it is 10 feet. So 5 feet, 5 feet. Here we have 100 pound force, and here we have 800 pound-feet moment. So beam A, B, C, it is cantilever beam. The length for this beam it is 10 feet. At free end point C is subjected to one point load. The magnitude of point load it is 100 pound. At point B it is subjected to concentrated moment. The magnitude of concentrated moment is 800 pound-feet. Find reactions for this beam, draw shear force diagram and bending moment diagram. Next one is simply supported beam subjected to two concentrated moment L over 3, L over 3, L over 3, A, B, C, D. We have two concentrated moment M and M. Magnitude equal, but the direction it is in opposite direction. Find reactions, draw shear force diagram and bending moment diagram. The last one, it is this beam. Here you see this support cannot sustain to shear force here, so the reaction, force reaction here is 0, but bending moment reaction we have it, but shear force reaction is 0. Here we have roller support, so point A, point B. The length for this beam L, it is subjected to uniform distributed load. The intensity of the load it is W naught. For this beam, find reactions. I already found that. Several lectures ago I find reaction for this beam, but you can double check. Find reactions, draw shear force diagram and bending moment diagram for this beam. These are your homework problem for next session. Thank you so much for watching this lecture. See you next session. Bye bye.